In this video, we're going to talk about the many worlds interpretation of quantum mechanics. This is one of many interpretations, and we'll discuss some of the others later, but it's intended to solve one of the most famous problems, one of the most famous philosophic problems with quantum mechanics, the measurement problem. The measurement problem, in a nutshell, is the question of exactly when, where, and how measurements occur. So we know in quantum mechanics there's two types of equations. One which describe the wave function, the function that describes the wave, and one that describes what happens when you measure that wave. But what exactly is a measurement? So at the microscopic level, there's no such thing as a measurement. At the microscopic level, we just see evolving waves that just keep changing according to the equations of quantum physics. So in this example, we have beam splitters. A photon hits one, it gets split, one heads up, one heads down, hits the next two beam splitters, they head up, they head down. So we end up with, 25% chance of each of those branches having the particle in it when we measure it. But what is a measurement? If we put some sort of other particle in the way to detect whether or not there's a photon there, then it just continues to evolve according to the laws of quantum mechanics. And then there's just a 25% chance that the photon is now entangled with some other particle and that the other particle will be there. So a macroscopic detector like a light or an arrow on a machine or a sound, something that tells us that we've found the particle there, is never in a superposition at the macroscopic level, but it's composed entirely of quantum particles. So if you followed the Schrödinger equation through, the equations of quantum mechanics, you would find that even if you built it up to a macroscopic level, there should still just be a 25% chance of finding the pointer, indicating that it's either one, the other, or the other. So the pointer should be in a superposition. But we never find it that way. We only ever find it in one position. So what is this mysterious measurement thing? So let's consider that in more detail with a real example. We'll use a photomultiplier tube, which measures whether or not a single photon has been detected, and at the end on the right-hand side it would light up a light, or it would do something that would indicate that this single photon has been detected. So on the left-hand side we have a photon, a high-energy photon coming in, which might have been a photon that came through one of our beam splitters from the previous slide, gets converted through to low-energy photons, hits this photocathode, which in turn releases an electron. The electron hits one of these diodes, and that converts it to a couple of electrons. That hits another diode, which turns it into even more electrons, and then we just cascade more and more and more and more until finally right at the end we have enough energy to send through our connector pins and do something macroscopic like light up a light. So the measurement problem says, okay, now where exactly in that process does it convert from being a probability? So that first high energy photon might only be, say, 50% chance of detecting a photon there. So when does it convert from being a 50% chance to being a 0% chance or a 100% chance? So that's the question. Is a measurement when it gets converted to an electron? And we know that's not right because we know single photons, we can use the equations of quantum mechanics and quantum field theory to tell us when an electron gets created, gets ejected from this photocathode. But again, the equations still tell us that there's only a 50% chance. If there were a 50% chance of the photon, there'll only be a 50% chance of finding the electron. What about here when it turns into more electrons? Well, they're the same thing. We can still run equations at this level with even a few electrons. We can still run the equations and they will still be a 50% chance of finding those electrons there. What about all the way at the end? Again, the same thing though, we just keep running it forward. By the time we get to the end, we have so many electrons that our classical machines couldn't possibly calculate all the interactions between those electrons. But we know we just scale up the answer from the first few, and we know lots of electrons behaves in the same way as just a few electrons. The rules are the same. So we know that the laws of quantum mechanics don't tell us that anything has changed fundamentally there. So we still have this 50% probability of electrons funneling out of the connector pins. So is it in the light bulb somehow? But again, the light bulb is entirely ruled by the laws of quantum mechanics at this microscopic scale. So if we had a big enough, powerful enough computer to calculate all of this, that would still be in a 50% chance of being on and being off. Then the final question, is it here? Is it somehow in our eye or in our brain that this collapse happens? Again, our eyes and our brains are composed of lots of particles, so there just doesn't seem to be any exact point that the science would tell us that it's changed from a probability to an actual result. So here are a few of the answers that have come in over the years. What people call interpretations. The standard one is the Copenhagen interpretation, often being derided as just the shut up and calculate interpretation. And that is, look, whatever's happening, it's beyond our intuition, it's beyond our ability to determine where exactly this measurement is. The math works. We know macroscopic things behave one way and microscopic things behave another way. So just don't ask too many questions. Just do the calculations, apply the math, and the answer will tell you what you should predict. That's not satisfying to everybody. Another one over the years has been that consciousness somehow has this impact. So when it hits our eye, maybe when it hits our brain, maybe somehow our consciousness is involved. Now that doesn't feel a lot like science. And it is a bit old-fashioned now to think that consciousness somehow makes something happen to the wave function. But there is a bit of a resurgence. Programs like the Integrated Information Theory program of consciousness can be used to say, look, there's this exact mathematical formulation of integrated information that sits inside our brain. And some people want to say, well, once it gets to a certain level of integrated information, all of a sudden it can't be in a superposition. So there's some threshold beyond which it suddenly triggers this collapse. There's still a lot of work to be done and a lot of conceptual work to understand what that even means and why some particular threshold would make a difference. So it's growing, but it's still not one of the more popular interpretations. Bohmian mechanics is one of the more popular interpretations, that there are somehow pilot waves that guide particles around. Bohmian mechanics is nice because it's entirely deterministic. There's no collapses. We don't know the exact position of a particle, and these pilot waves just move it around. The pilot waves themselves are non-local. They affect each other through space, through any distance in space. And we just don't know which one contains the particle until we measure it. And then when we do, these pilot waves affect each other. So it's a method that works. It has a few extra rules than standard quantum mechanics because we need to know about these particle positions. And a few people have pointed out that these pilot waves have to evolve in a way as though there were particles in all of the waves. And that means that while the particles aren't necessarily taking up multiple superpositions, these waves are still taking up superpositions. So there's still a wave that looks exactly like you or me doing other things in other worlds, in other parallel worlds. So some people have suggested that maybe Bohmian mechanics itself is just a different guise for the many worlds interpretation, which we'll be talking about. Objective collapse, again, if you add some more rules, you could say there's some small random chance of a collapse, and if something does collapse, then it spreads with entanglement. So as soon as you've got a lot of particles, which you would in any macroscopic object, that small random chance means that it's almost definite that big objects are going to look like they're not in a superposition. So, it has some things going for it, but again, there's this question of exactly when does this objective collapse happen? What is this small chance? So far, we've never seen it. At the moment, we're sort of looking for that value, and objective collapse would be disproved if we just kept putting things in, bigger and bigger things in superpositions. we would know that there is less and less chance that that theory is true, because we'd be putting more and more particles together, so this random chance should show up. And we know we're putting things that are almost as big as microscopic, things that are the width of a hair, we're putting those into superpositions at the moment. So we're starting to get big enough that this looks like it may or may not be a theory, but at least it's objectively provable or disprovable. Retrocausality, there's also some other theories that somehow the future can impact the past, and that is in particular the measurement device, the settings on the measurement device that we're using can somehow influence whether or not the particle is released there. So even just putting a detector up will influence whether or not a particle is released one way or another. This again has some following. Some people don't like backward in time causation, so they're not as happy with this. But it is a working theory that works well with the math of quantum mechanics. So Everett's theory, Hugh Everett III's theory, was that maybe there is no measurement collapse. So he proposed that maybe the superposition just does continue to build up and up and up. And we have the famous Schrodinger's cat paradox, which at the time, Erwin Schrödinger proposed to sort of show how absurd it was to think that, that these quantum effects would scale up. But this is a good example that demonstrates Hugh Everett's thinking, that the traditional Schrödinger's cat example is that there is a radioactive particle in the box on the right there. It has a 50% chance, say, of decaying in an hour. We leave this cat in there for an hour. If it decays, if that particle decays, it drops a hammer. The hammer smashes a vial of poison, and the poor old cat dies. But if it doesn't decay, which it doesn't do with a 50% chance, then hammer's still up, cat's fine. So in an hour's time, the question is, what's happened to the cat? Now, traditionally, we would think the cat's either dead or alive, but the quantum mechanical answer would be that the cat's in a superposition of being dead and alive. All we know is that there's a 50% chance that it's dead, 50% chance that it's alive, and it's not until we look in the box that we see that it's dead or alive. But Hugh Everett said, well, what if it just continues? What if it really is the case that the cat is both dead and alive at the same time, but then when we open the box, we join it in the superposition, and the superposition just continues out. So let's break that down a little more. So we start off with a particle, a cat, and a person. That particle either does decay down the bottom, or it doesn't decay and it's blue and it's fine up the top. When that first happens, we still have the cat and the observer, the person who's going to look in the box. They're fine, they're still, cat's alive, person's still fine, not in a superposition. Then that particle makes its way, its effects of that particle make its way to the cat, and then the cat is either alive or dead, depending on which of those outcomes occurred. But to the cat, there's a cat that is either alive or a cat that is dead. So from the cat's perspective, in each case, there's only one outcome, one that it's there and one that it's passed away. So the observer then looks in the box, and the observer joins the cat. So there's one observer now that sees the live cat, and there's another observer that sees the dead cat. So the observer is just in a superposition, but to each of those observers, it looks as if only one thing has happened. It looks either that the cat is alive, or the observer never sees a superposition of cats. It never sees the cat dead and alive at the same time. It just sees one or the other. It's just that there's now two observers. So the way that we can think of this, like we thought earlier in some of our earlier videos, is about this splitting wave. So we have one wave which is composed of two components. Something happens to it and it splits that wave into its two orthogonal components. Orthogonal meaning, in the case of that diagram there, perpendicular. So it splits it into its two components. They separate from each other, go their own separate ways, and then do their own separate things, and then stop interacting with each other anymore. So that's the sort of picture that we have of these splitting waves and splitting sets of observers. So what does this mean? Going back to Einstein, Einstein famously had some quips about quantum mechanics. There was a number of them, and the measurement problem was just one of them. So this is a great litmus test for any of these interpretations. You know, does it solve all of these worries that Einstein had? So the first one, about measurement problem, he quipped, is the moon there when nobody looks? He was making the point that, you know, surely the moon must be in one state or another state when nobody's looking at it. It can't be sort of in this fuzzy halfway house state. It must be in one or the other. So the many worlds interpretation clearly solves that. We know exactly that the moon is there, and that we know that the act of actually looking at it doesn't change the moon. But if the moon was somehow in a superposition, it might change us. Also, Einstein didn't like the fact that quantum mechanics was not deterministic, that there were random elements in it. He'd say, God does not play dice, a very common phrase that he repeated over and over again. Again, the many worlds theory solves that problem. So it is a fully deterministic theory. Never at any stage do we have any random collapse happening. And non-local entanglement, he said famously that it was spooky action at a distance, that you might be able to have two particles separated from any distance and you measured one and something instantly happened to the other. So this interpretation also means that just measuring something in one place doesn't change anything at a distance. So the thing at a distance still goes on, it still evolves according to the Schrodinger equation. You never have doing something at one place instantaneously affecting doing something at another place. It's not till the two things come back together that they start to realize that they are correlated or not correlated in one world or another world together. So, you know, interestingly, this does stack up against a lot of these concerns. So in a final slide, we'll just think about some of the big questions that are often asked about the many worlds interpretation and just give a few broad brush answers. So commonly asked, does this mean there's a different me for every choice I've ever made? And this is the basis of a lot of science fiction movies and whatnot. But the real answer is that it's probably not the case. Strictly speaking, it's quantum events that cause the splitting. So like going through a beam splitter or doing something that would cause something to have a probability of being here or there, not really a choice. These are like so microscopic, these are happening at the particle level. And as such, when they build up, when you get billions of particles, a lot of the effects will cancel each other out. So at a macroscopic scale, you might not see much difference, even though at a microscopic scale, you have lots of splitting and lots of differences. At the macroscopic level, they might all just sort of smooth each other out such that you see more or less the same thing. So these macroscopic choices, blood flowing through our brain, neurons firing in our brain, all of these things are probably very little affected by the microscopic goings on of any one particle. However, in some cases, they can be blown up to larger scales. So, you know, we know, for example, that just one photon could push a skin cancer over the edge and, you know, cause you to get a cancerous growth. So, you know, it could change the course of your life. These quantum events could change the course of your life. But it's not necessarily always the case that just because you make a choice, that's the thing that causes the universe to split. It's in fact these quantum events, these waves that are continually splitting each other, that's actually causing the splitting. So second question, are there infinitely many copies of me out there? There's a little bit of work that's been done. I recommend you look at Sean Carroll's book, Something Deeply Hidden. He does a little calculation in there that shows it's probably not an infinite number of copies, but it certainly is a very huge number. For some people, that is the most problematic part of this theory, that there's this huge number of alternative versions of me and a huge number of alternative versions of the universe. Again, for some people, that's a deal breaker. Ontological extravagance, as they call it. But for some people, that's not the deal breaker, because we have so many atoms in our body that we can't possibly conceive of large numbers. There's so many stars in the sky, we can't possibly conceive of those large numbers. Time is huge. Space is huge. Everything, there's a lot more of them than we initially thought. This is just another huge number on top of all those huge numbers. So, maybe it's not a problem. I'll let you be the judge of that one. Now, could we interact with these other worlds? That would be great, but the answer is unfortunately no, because the parts that we split into, the universes we split into, don't interfere with each other. Just as we saw with those splitting waves, these waves in the universe also move apart from each other and don't interfere. The only way we'd be able to interfere is if we put them all back together again, if we reversed all of the processes. But if we did that, we would reverse all of the memories we created, and we'd just reverse out anything that we'd done. And that's the only way we could get back to a situation where we could start to interfere with each other again. That's unfortunately the laws of quantum mechanics. That's the laws of these wave splitting. Until and unless somebody can come up with something clever, for the moment, we actually don't think that you'd be able to interact with these worlds. So that leads to the obvious question, well, can we prove it then? If we can't interact with the worlds, how will we ever know? It's a very good question, a very interesting question, and the answer is who knows. There have been some experiments proposed. David Deutsch proposed an experiment with artificial consciousness, where you would put it into a superposition and you would undo its memories, but you would do things while it was in the superposition that could only be done when it was in the superposition. So the artificial consciousness wouldn't remember, but we would know whether or not it had been separated. But that's in the very far future, of course, because artificial consciousness is not something that we can make yet. And on the flip side, while we can't prove it, we certainly could falsify it easily. We're putting things in bigger and bigger superpositions, as we saw before. So if at some stage putting things in superpositions just starts to break down, if we figure out what makes macroscopic, and microscopic, if we get to some stage where we put bigger and bigger things in, and then we put something that's the size of a marble into a superposition, we find we just can't, then all of a sudden we know that the many worlds is false, because you couldn't put something like a human being into a superposition. So far we haven't reached that level yet. So far we haven't seen anything that breaks this rule of superpositions, but it is entirely possible in the future that we will see exactly that. So it is actually falsifiable, even though it's not provable. And mind you, the laws of science are not generally provable things. They're always something that you can disprove, but they're never something that you will absolutely always guaranteed 100% know to be true. There's always room for somebody to come along and do some new experiment that proves them false. I hope that's been a satisfactory tour of the many worlds problem, and we'll move on to the next big problem in the next video.